Hey y'all, I'm Matt Byrne, and in this week's Do-It-Yourself lab, I chose to observe the oscillations of a yo-yo string with the forces of tension acting on it. And introducing this lab, I wanted to explain the background of a yo-yo. So it's a great example of an object with a high angular velocity, which then in turn yields to a high angular momentum. And that's what keeps the yo-yo balanced and free spinning as you're going along with a trick. And Eli hops is a specific trick that will be observed during this lab as the yo-yo bounces straight up and down, and it's from a snapping motion created by the string as the thrower's hands expand and decrease in distance apart, and creating a motion where the yo-yo bounces off the string, which will be shown in the next slide. And kind of when you look at this as a physics perspective, the speed of that yo-yo has to be extremely fast in order to create the velocity. Therefore, the snap has to be creating a force. So what we're looking for is the force that the yo-yo is experiencing, and therefore what's required to create the pop of the yo-yo. So essentially, the force required for the escape velocity. And these are some examples of yo-yos. This is a yo-yo in any type of trick. So this is me doing a yo-yo trick outside of my dorm, and this is just a random trick just to show what a yo-yo is capable of doing. This is the example of the angular momentum, keeping it balanced. And this is Eli hops, in which the yo-yo bounces straight up, and you can see how the hands will come together and they separate as the yo-yo pops. So the fundamental physics behind this, this is your position initial, where hands are at a maximum distance apart, the radius. The string is very taut. There is not much leeway going. And this is the point where string tension is also at a maximum. So therefore, this is the force. And at this point, it's when the yo-yo is going in an upwards motion. This is radius minimum, where the yo is at its highest point in its position of travel. And for this lab, we're going to say that the length of the string has no effect on it, but it reaches its y max because of gravity. And this is its intermediate phase, where this is where it starts at an initial position, where this is an average of the length between the minimum and maximum, and that's what creates it for the 3 points to rest. The tension on the string can be found using the standard tension formulas. So we can find the force that the yo-yo is exerting on the string by the mass times the acceleration of gravity, which is extremely small mass in kilograms, and therefore it's creating barely or a little over half a newton of force. And using some trigonometry and geometry from the observed video on the next slide, we can find the distance of the string and the angles from which they're at. So right here we have tension of the measure of 1 and tension of 2, and on this one, this is the part of the string that is tension 1, and this is tension 2. This part of the string has no effect on it, and that part of the string is this one right here. So we're looking at this force and that force of tension. And at these angles, these are the two combined tension forces that are keeping the string at its initial position. And here's the tracker software to show it. This is only one Eli hop. You can see that the yo-yo reaches its maximum height right around here in around frame 10, and it starts to decrease almost in its identical path on its upward trajectory. And the force pushing the yo-yo up is the snap that I was mentioning, created by it. It's projectile-like, so we can use the kinematics equation of y max down here. This is right here, it's velocity initial times the time, which we can find just from counting the frame rates of that photo, gravity times time squared 1/2, and this is where it comes right here. And its initial velocity is actually found from reworking the force applied back in the last 2 slides. This is its velocity at its initial point that it's leaving at. So at this position, it is at this velocity. So the difference in this position and that position, we're counting as just the force and the acceleration acting on it. So that is what this math is. Therefore, we can then work mass times acceleration. So if we have its acceleration in its time interval, so if it started at 0 and it got to 5.6 meters per second, Then we divide that by its time, and that's its acceleration rate, which we found here at 80 meters per second, which sounds extremely fast, but if you rewatch the video in live, it is moving very fast in order to get that yo-yo going. So it's only because it's on such a small scale that you wouldn't think twice about it. Therefore, we can find that the force acting on the yo-yo at its final form is almost 5.5 newtons. So, concluding this experiment, we can kind of tell that the speed at which the thrower will expand his hands does have an effect on the velocity. If the yo-yo expands his hands, that means that there's a lesser time interval. And if there's lesser time, that means acceleration is greater. And as shown in the last slide, if acceleration is greater, therefore force is greater. They are directly proportional of one another, modeled by the equation F equals ma. In this lab, obviously, since I was doing one of my own passion, this was not predetermined. Human error can be greatly factored in, and that's why at the beginning I mentioned that the length of the string is not going to be counted as a variable, so we're going to measure this simply as it's reaching y max because of gravity, not because of string length, which is relatively accurate, but it is something that just needs to be said. Otherwise, this is a naturally generalizable phenomenon.